Yeah, my name is Tristan Miller. I'm a postdoctoral research scientist at the Ubiquitous Knowledge Processing Lab of Technische Universität Darmstadt, which is a town in Germany, which is near Frankfurt. So just to give you some idea of what it looks like. So this is the university here. And this is our office right there. So anyway, the Ubiquitous Knowledge Processing Lab is headed by Professor Irina Gurevic, and we're focused on natural language processing and computational linguistics. Our main research areas at the moment include argumentation mining, language technology for the digital humanities, lexical resources and algorithms, text mining and analytics, and writing assistance and language learning. And probably most of what I'm going to be talking about today involves the second and third items on the list here: language technology for the digital humanities and lexical-semantic resources and algorithms. And in case you might have noticed that I don't have a German accent. It's because I'm not German myself. I'm originally from North America. I got my undergraduate degree at the University of Regina, which you've probably never heard of, and my master's degree at the University of Toronto. In addition to doing research, I'm involved in some science popularization. I write for, and I'm on the advisory panel for a non-specialist linguistic magazine called Babel. So if you're at all interested in the science of linguistics, but you're not a linguist yourself, then you might want to check us out. You can visit us on the web at babelzine.com, or just Google for Babel, the language magazine. We have all kinds of interesting stuff all about language and linguistics, various languages of the world. So moving on to my actual research talk, here's an overview of what I'm going to be speaking about today. There's basically going to be two main parts. First, I'm going to be talking about computational word sense disambiguation, that is, how to get computers to recognize the meanings of words in context. So I'll discuss the pros and cons of various WSD approaches, and then I'll go into more details about some of my own research projects. And the second part of my talk, I'm going to be discussing how word sense disambiguation can be applied to the computational processing of puns and wordplay. A pun is like a word that's used in an ambiguous manner usually for a humorous purpose. So let's begin. Well, polysemy is a fundamental characteristic of all natural languages. Writers, philosophers, linguists, and lexicographers have long recognized that words have multiple meanings, and moreover, that the meaning that a particular word carries depends on its context. So, for example, when I say the word bat in the sentence, "he hit the ball with the bat," I might be referring to the wooden club used in baseball or certain sports, or I might be referring to the flying nocturnal animal. Now, the process by which we decide which of these two meanings is the correct one in a given context is known as word sense disambiguation, or WSD. And in humans, WSD is largely automatic and unconscious. But for computers which lack our own real-world knowledge and linguistic abilities, the task can be quite difficult. And although computational WSD is difficult, it is nonetheless very important for natural language processing, with applications in a number of downstream tasks. So some sort of sense disambiguation, for example, is required for machine translation. Otherwise, a computer would have no way of knowing when to translate bat into German as Schläger and when to translate it as Fledermaus. So you can make similar arguments for many other applications, including information retrieval, information extraction, and writing assistance such as spelling correctors. But just what is it about WSD that makes it so hard? Well, much of the difficulty is due to the many ways in which the disambiguation task can be formulated or parameterized. So In some scenarios, it is every word in a text that needs to be disambiguated, whereas in other scenarios, it might just be all the occurrences of a single word. Some scenarios expect a WSD system to select from a list of senses provided by, say, a dictionary, whereas other scenarios would expect the computer to induce its own inventory of senses. Some applications are concerned with only one particular language or one particular domain within a language, whereas others may not be. And the critical issue here is that even very small variations in how the task is formulated can lead to very drastic changes in the approach and in the resources we need to use for the disambiguation. Now, a second source of difficulty with WSD has to do with the very nature of word senses. While computational WSD assumes that word senses are fixed and discrete, in reality, the boundaries between senses can be very hard to distinguish. So the sense divisions made by lexicographers, that is, the sense divisions that you might see when you open up a dictionary, are to a very large degree completely arbitrary, and they're often too fine-grained to be useful in a computational setting. A third main source of difficulty is the knowledge acquisition bottleneck. All WSD systems employ digital knowledge sources of some sort. Depending on the exact method, these may be machine-readable dictionaries and thesauri, or semantic networks, or manually annotated text corpora. However, manually constructing these lexical-semantic resources and training data can be extremely expensive. And moreover, it may need to be repeated each time the configuration of your WSD task changes. Now, a final and somewhat rarer source of difficulty is the fact that not all word occurrences are intended to be unambiguous. In many, if not all languages, there exists a class of rhetorical constructs known as paronomasia, or puns, in which lexical-semantic ambiguity is a deliberate effect of the communication act. WSD algorithms are commonly categorized according to the types of knowledge sources that they employ. Supervised techniques use machine learning classifiers trained on text to which word sense annotations have been manually applied. And though they are highly accurate, they are restricted to those languages and domains for which there exists a significant amount or a sufficient amount of training data. Now, in contrast to supervised techniques are knowledge-based systems, and they rely only on lexical-semantic resources such as dictionaries or raw unannotated corpora. And though this makes them of more general applicability, they tend to suffer from lower performance. And this is often due to the informational gap between the target word's context and the word meanings that are encoded in the dictionary or other LSR that you're using. So far in this introduction, I've identified a number of barriers to the construction of accurate WSD systems and to their implementation and evaluation. So first, there's the problem that knowledge-based WSD suffers from low accuracy due to the informational gap. So in this talk, I'm going to explain two ways for bridging this informational gap. The first way explores the contribution of distributional semantics, and the second way explores the use of aligned lexical semantic resources. The second problem is that the distinctions that dictionaries and other resources make between word senses are often too subtle for computational WSD. Now, I'm going to show how we can use the aforementioned alignments between lexical semantic resources to coarsen these sense inventories, making them more useful for certain disambiguation scenarios. And a third and final problem is that most disambiguation systems to date are incapable of processing deliberate lexical-semantic ambiguity. That is the kind of ambiguity that we would find in wordplay and puns. So today I'm going to talk about how WSD can be adapted to puns. So that concludes the introduction to the talk, and I'm now going to be talking about my work on bridging the lexical gap for knowledge-based WSD. So dictionary-based disambiguation began in the 1980s when a researcher by the name of Michael Lesk proposed that two words in context could be disambiguated by looking up their respective definitions in a dictionary and then finding the maximum lexical overlap between each pair. And a popular variant of this technique, which is known as simplified LESC, allows us to disambiguate one word at a time by comparing its definitions to the context in which it occurs. So let me give you an example of this. Let's continue with this bat example that I introduced earlier. Now, the simplified LESC algorithm would start by looking up the senses of the word bat in a machine-readable dictionary. And it would then count the number of words that each definition has in common with the context. So in this case, only the second definition has any words in common, so it would be selected by the LESC algorithm as the correct sense in this context. Now, even though LESC algorithms are conceptually simple, they're actually surprisingly accurate, at least for the case where at least some sort of lexical overlap can be found. However, as you might imagine, this condition doesn't always hold. Because the context and the definitions are usually quite short, it's often the case that there are no overlapping words at all. And we call this problem, we call this type of informational gap the lexical gap problem. So for example, say we want to disambiguate the word interest in the sentence here, the loan interest is paid monthly. Well, again, the algorithm would look up the word interest in a machine-readable dictionary, and it might find the two definitions listed here. But in this case, none of the words from the definitions occur in the context and vice versa. And therefore, the LESC algorithm would be unable to make any particular sense assignment. So, how can we bridge this lexical gap? Well, one way would be to expand the context and the definitions with additional relevant texts, thus increasing the possibility of lexical matches between the context and the definitions. So before I go into details, I just want to illustrate the idea behind this approach. So let's return to this interest example. Again, we see here the definition here on the bottom and the context at the top, and there are no words in common at the moment. But what if for every content word in the context and every content word in the definition, we had a list of, say, 10 similar words? So we could then add these lists of words to the definition of the context, thus increasing their size by quite a fair bit. And not only that, but now with this expanded representation, many of the words that we've added to the definition now occur in the context and vice versa. So it looks like, intuitively speaking, an overlap-based method should be able to use this to successfully disambiguate text, or at least it works in this example. So this seems like a good idea, but where can we actually get these lists of similar words? Well, in this work, we get them from something called a distributional thesaurus, or DT, which is basically a resource that provides related lists of similar words for every word in a lexicon. It's similar to a print thesaurus that you may be familiar with, except that the word lists aren't categorized as to whether they are synonyms or antonyms or other relations. They're just a list of words that are somehow related. And the big advantage that these distributional thesauri have over the traditional print ones is that they can be constructed entirely automatically. A computer can read in this huge unannotated raw corpus, say from Project Gutenberg or from the internet or something like that, and then with very little or no linguistic preprocessing at all, it can analyze the patterns of co-occurrences and produce the thesaurus. Now, the idea behind DTs is something called the distributional hypothesis, which basically states that words which appear in similar contexts tend to have similar meanings. This hypothesis was first popularized in the 1950s by J.R. Firth, and it was subsequently refined to account for Ferdinand de Saussure's notions of syntagmatic and paradigmatic relations. Now, distributional thesauri aren't the only way that distributional similarity has been applied to word sense disambiguation. The distributional hypothesis is also at the heart of some long-standing heuristics used in WSD, as well as the vector space representations such as latent semantic analysis and LDA, which you may have heard of. However, DTs do have a number of advantages over dense vector representations. So one potential problem of dense vector representations is that they are very opaque. That is to say, they consist of huge matrices of numbers that are not easily understandable by humans. So when these models fail, it can be very difficult to do some error analysis and find out why. Another problem with vector space models is that the semantic neighborhood in which they situate each term may contain a lot of words that, while they are genuinely similar, are nonetheless too infrequent to be realistically useful for the lexical overlap type approach that I'm proposing. So for the work that I'm about to describe, we used a distributional thesaurus which was constructed for a previous research project. And in that project, an unannotated 10 million word web corpus was automatically parsed just with an off-the-shelf parser. The collapsed dependencies were then used to extract features of words, which I'll show on the next slide. And these features were counted and they were ranked according to their significance and then pruned to the top 300. So the similarity of two words after that could be measured by counting how many features each of the words have in common. So across all parts of speech, our final distributional thesaurus contains at least 5 similar terms for a vocabulary of over 150,000 English words. Though the nice thing about the system is that it's very easy to construct the DT in any language you want. So this slide here gives some idea of what the DT actually looks like. So this is an excerpt for the noun paper, which shows the two most similar words, which happen to be newspaper and book. And it also shows the features which newspaper and which book have in common with the noun paper. So for example, if I can explain, this first one, told, means that the word newspaper is often found as the direct object of the verb told, and so is the noun paper. Or with book, book is frequently modified by the adjective recent. You might say recent book, but you might also say recent paper. So basically, if you count up all these shared features, we see that out of the 300 most salient features, the word newspaper shares 45 with the noun paper, and the word book shares 33 features with the noun paper. So once we've constructed our distributional thesaurus, we apply it in much the same way that I already demonstrated. We simply expand each occurrence of every content word in the context and every content word in the sense definitions, other than the disambiguation target itself, with the top n entries in the distributional thesaurus. And since we don't at first have an intuition of how many lexical expansions would help, we tried various values of n ranging from 0 to 100. Now, we don't do any stemming or lemmatization or stop word filtering or basically any linguistic preprocessing of the context and the definitions, because the distributional thesaurus itself, it's not lemmatized or stemmed or anything like that. Now, in the unlikely event that 2 or more senses share the highest overlap with the context, we simply choose one of the senses at random. And what are the results? Well, we tested our various configurations of our algorithms on an English language data set from the SemEval 2007 workshop. And you can see here that the results in this graph, where the red line is the simplified LESC algorithm, the one that I went through before as an example. And the blue line is a slightly more sophisticated version of the LESC algorithm known as simplified extended LESC. And the reason it's more sophisticated is that it already enriches the sense definitions using a different way. So the base system, without any lexical expansions, that's shown, right here. So this is the basic simplified extended LESC and the basic simplified LESC. And they get about 68% accuracy and maybe 79% accuracy, respectively. However, as we add more and more expansions, you can see that the accuracy goes up in both cases, though the effect is less pronounced for simplified extended LESC. Nonetheless, by using 100 lexical expansions, we were able to effect a relative improvement of over 10% for simplified LESC and over 2% for simplified extended LESC. So to put things in context, here's a table that shows the results of our systems along with those of some naive baselines at the top and some state-of-the-art systems at the bottom. So the random sense baseline, this simply disambiguates words by looking the senses up in a dictionary and picking one at random. So a very stupid one. And the most frequent sense baseline, MFS, this works by always selecting the sense that occurs most frequently in SemCore, which is a large manually annotated corpus. And the reason that I've graded out in this table instead of setting it in black is that it is a supervised baseline. It actually needs manual annotations to work. So it's not directly comparable to the knowledge-based systems that I've listed here. However, I'm listing it here anyway because it's a very hard baseline to beat even for supervised systems, even for machine learning classifiers. For the state-of-the-art systems, we have Anaya Sanchez, which was the best performing knowledge-based system at the original SemEval 2007 task, and it uses some sort of a clustering approach. And the other three systems are more recent. They variously used topic models, graph theoretic approaches, and word embeddings. Now, as you can see, our lexically expanded algorithm actually outperforms all of the state-of-the-art system and, surprisingly, even the supervised baseline. And when you break down the results by part of speech, noun, verb, adjective, adverb, we can see that our system has state-of-the-art performance on adjectives and nouns, which is pretty good. So I'll now describe a different approach for closing the lexical gap in knowledge-based WSD. And this one relies on the fact that different lexical semantic resources often divide up word senses in different ways and use differently worded definitions even for the same word senses. And you can try this yourself. Just open two different dictionaries and look up the same word, and you'll find these different dictionaries tend to use different numbers of senses and describe them differently. So if we could match up corresponding senses from several different dictionaries, or LSRs, then we could combine the sense descriptions, providing a lot of extra lexical material that we could use to compare against a word context. Now, this actually isn't a new idea, but one of the reasons that it's not done more often is that aligning LSRs is a very hard problem. And it's actually hard precisely for the same reasons that make it attractive for our purposes, namely that there is no one-to-one mapping of senses between dictionaries, and that the sense definitions can be very, very differently worded. It's also hard because the content and structure of LSRs varies a great deal, and many alignment algorithms were written with very specific dictionaries or LSRs in mind. So our solution is to take existing alignments between pairs of resources and then automatically merge them. And this way we don't need to bother with creating our own specialized alignment for any given pair of resources. We simply exploit existing ones by combining their output. So we do this in 3 steps. First, we collect existing pairwise alignments that share a common resource. So for example, there exists an alignment produced in 2011 between the semantic network WordNet and the online dictionary Wiktionary. And there exists another alignment from the year 2013 which links WordNet to Wikipedia. So if you actually download these alignments as they're distributed by their authors, you'll find that they just consist of text files that are pairs of unique sense identifiers. So each of these identifiers refers to a particular sense of a word in Wiktionary or in WordNet or in Wikipedia. And what you see on the screen is just a very small portion of these text files that were distributed by the authors of the alignments. So the next step for us is to conceptualize these pairwise alignments as a graph. So we consider the unique sense identifiers from each resource to be vertices in the graph. And then the sense pairings given by the alignments become the graph's edges. So finally, we run an algorithm that identifies all of the connected components in the graph. And note that because the original alignments were not one-to-one, this step also has the effect of clustering together senses from the same resource. And this turns out to be very useful for pun interpretation, which I'm going to be talking about a little bit later in the talk. But for now, simply observe that each WordNet sense in the middle here gets connected to one or more senses in Wiktionary on the left or Wikipedia on the right. And we can therefore expand those WordNet sense definitions with the definitions from the connected senses and then apply the same lexical overlap WSD method. And that is, of course, exactly what we did. This slide shows various performance metrics for two different lexical-like disambiguation algorithms with and without the enriched sense representations. So the top half of the table is for the regular simplified LESC algorithm, and you can see that with the enriched sense descriptions, accuracy, or recall as it's called in WSD, increases by a modest but statistically significant amount. We also tested these enriched sense representations using the lexically expanded LESC algorithm that I covered in the earlier part of the talk. And here we actually get, interestingly, a decrease in accuracy, going from 52.71 down to 50.44, which suggests that the two methods are not actually compatible with each other. So moving on, in this part of the talk, I'm going to present how the research that I've described up until now can be adapted to the relatively new task of pun interpretation. So, as I mentioned before, traditional approaches to word sense disambiguation tend to rest on the assumption that there exists a single, unambiguous communicative intention underlying every word in a context. However, there exists a class of words known as paronomasia, or puns, in which the lexical-semantic ambiguity is a deliberate effect of the communication act. That is, the writer or speaker intends for a certain word to be interpreted as carrying separate and contrasting meanings. So one example that often pops up in the literature is this supposed message from a power company to a delinquent customer. We would be delighted if you send in your bill. However, if you don't, you will be. Now, just out of curiosity, does anybody see the pun here? It's a bit tricky, maybe especially if English isn't your native language. No? Okay, for the benefit of those who didn't get it, the pun here is on the word delighted. So the first and most obvious sense of the word means greatly pleased. I'm delighted to see you. But it can also be analyzed as applying the prefix D to the verb light. D-light, meaning to remove the light. So the power company is threatening to cut off the customer's electricity if he or she doesn't pay his bill. So this example may seem a bit, frivolous in isolation, but puns are actually a surprisingly common and even expected feature in many types of discourses. Shakespeare's plays, for example, are very famous for their use of puns, where they occur with a frequency of about 35 puns per 1,000 lines, even in the tragedies, indicating that this isn't limited to humorous texts. Puns are also particularly frequent in film and television comedies, where they pose tremendous problems for translators. And they're also regularly seen in advertising, where they're used to induce a certain positive or negative attitude towards a target. And the automatic interpretation of puns, therefore, has applications in sentiment analysis and literary analysis in the digital humanities, and of course in machine-assisted translation. As well, it's also applicable in human-computer interaction, where studies have already shown that computational generation and recognition of humor can be very important. One of the main questions in my research, therefore, is how can we adapt techniques from WSD to deal with puns? Well, to investigate this, it was first necessary to construct a large annotated data set of puns. So what we did is we sourced a large number of puns from various online and printed collections, and also some contributions from professional humorists. And to keep things relatively simple, we restricted ourselves to homographic puns, which means basically that the two meanings of the pun, the word had to be spelled exactly the same way, more or less. So in the end, we collected about 1,600 instances, to which 2 human annotators and 1 human adjudicator applied senses from WordNet. I'm not sure if I introduced WordNet. It's basically a large semantic network similar to a dictionary, but with more connections between the senses and words. And we created a special annotation tool, which you can see here, that, well, maybe you can't see it very well, but it's there. It allowed the annotators to separately annotate each of the 2 meanings of the pun. So our data set turned out to have a relatively good inter-annotator agreement, Krippendorf's alpha 0.777. And on reviewing the annotations, a significant observation was that puns tend to transcend part-of-speech distinctions. That is, one of the sentences of the pun might be a noun, but the other one might be a verb or an adjective. So next it was necessary to adapt some WSD algorithms for use with puns. The low amount of annotated data rules out supervised approaches, so we decided to use the same knowledge-based approaches that I've already discussed earlier in the talk. So the most straightforward way of adapting these algorithms for use with puns is to simply, instead of selecting the best scoring sense from among the definitions, is to take the 2 top scoring senses that are returned. So for example, with simplified lesk, the first sense of the pun would be the definition that has the highest lexical overlap with the context, and the second sense of the pun would be the definition with the second highest lexical overlap with the context. And we also devised some pun-specific adaptations, which were tested with the simplified extended lesk algorithm. So these adaptations were basically means of solving ties between top-scoring senses. For the adaptation that we call POS, we preferentially select senses that match the pun's putative part of speech. So that is, we run a part of speech tagger over the context, and whatever that part of speech tagger says the part of speech of the pun is, we make sure that at least one of the senses selected is from that part of speech. And this adaptation is basically meant to account for this finding I mentioned that puns tend to transcend part of speeches, or parts of speech rather. The second adaptation is informed by the prevailing linguistic theory of humor as formulated by Victor Raskin and others, which holds that humor derives from the resolution of semantic incongruity. And in order for such incongruity to exist, the 2 meanings need to be sufficiently dissimilar. So for example, in listing the senses of the word bank, some dictionaries might make a distinction between bank, the financial institution, and bank, the building in which a bank is hosted. However, I can say with absolute confidence that no one ever in the history of punning has ever made a pun that rests on the distinction between these 2 senses of bank. And so if we're going to be interpreting puns computationally, we need to make sure that the system does not select senses that are so similar in meaning that they cannot possibly be used in punning. So fortunately, the work with the alignments that I described previously gives a very handy way of discriminating between semantically contrasting word senses. So say we want to identify the double meaning of bank in this punning joke. Where do otters keep their money? At the bank. I'm not sure what the word otter is in Russian. Does anyone know? Katya? You know the word otter in Russian? Okay, well, something unpronounceable to my Anglophone self. But Vudra. Vudra, okay. So an LSR such as WordNet might actually give us the following senses, and I've shown a bit of the definitions. So if you look up bank in WordNet, it'll say sloping land, a long ridge or pile, an arrangement of similar objects in a row, a financial institution that accepts deposits, a building in which the business of banking is conducted, a flight maneuver, blah, blah, blah. And if we apply some automatic WSD algorithm, possibly but not necessarily an overlap-based one, we might end up with the following scores for each sense. And we can see here that while there is a single top scoring sense, which is here, this gets 7 points, a financial institution that accepts deposits, there is a tie between the second highest scoring senses. So how do we resolve this tie? Well, since we had previously aligned WordNet to some other LSRs and induced a clustering over WordNet senses, then we can use these clusters to resolve the ties. So that is, we can say that once we have selected the top scoring sense from one cluster, then we cannot break the tie by selecting another sense from the same cluster. And in this particular case, our method rather helpfully does end up selecting the correct sense. Sloping land, especially a slope beside, well, the next words are a river, I guess. So here are the results of our naive and pun-specific disambiguation algorithms on our pun data set. The cluster 3 line uses the three-way alignment that I covered earlier in this talk. And cluster 2 uses a two-way alignment between WordNet and another online resource called OmegaWiki. Now the first thing to note here is the abysmally low baseline scores. So we're getting, with the baseline algorithms, only something like 9% or 13% accuracy for the random and MFS baselines. And this is, well, in traditional WSD, if we were assuming that there was only one correct sense per word, we would expect a random baseline accuracy of somewhere between 30 and 60%. So we would expect MFS to reach maybe 65%, maybe even 80. So this really underscores just how difficult a task the pun interpretation is. Now the low accuracy also extends to the basic LESC algorithms. However, when we modify these basic algorithms with these pun-specific adaptations, we see some very dramatic and very statistically significant improvements. Simplified extended LESC increased recall from 8, where do we see here? Oh yeah, from 8.47% to 14.10%, roughly, making it statistically indistinguishable from the supervised MFS baseline. Now, considering that this was actually, to my knowledge, the world's first pun disambiguator, that's a pretty promising result. So to summarize so far, I presented a first stab at a method for the automatic semantic interpretation of puns, provided, number one, that the word in question is known a priori to be a pun, and number two, that the pun is homographic or perfect, that is, the two words are spelled exactly the same way. Now, besides making this existing method more accurate for its intended purpose, there are some obvious ways in which the scope can be significantly expanded. So the first of these would be to eliminate the assumption that the location of the pun is known. That is, rather than having a computer tell us the two meanings of a pun, we need to first get it to recognize that a pun exists in the first place. Now, I've only made some very basic investigations into this, but I think this is a somewhat harder problem, though I think I may have been proved wrong on this, but I'll get to that later. The second way of expanding the problem is to account for puns which are imperfect, meaning the two words of the pun are spelled differently. Now, as it happens, there is a bit of prior work out there on the computational modeling of imperfect puns. So I'll give a little bit of background on this before wrapping up my talk. So the simplest way of characterizing the relationship between the surface form of a pun and its latent target is the strictly binary opposition between identity and non-identity. That is, are the two meanings of the pun spelled or pronounced exactly the same way, or are they not? So when we're talking about the phonological forms, that is the spoken form of the pun, the distinction is something between homophony and heterophony. And when we're considering the written form, the orthographic form, the distinction is between homography and heterography. So the examples here show that puns can be homophonic, heterophonic, well, homographic, heterographic. They can be both or neither, basically. Now, when we speak of an imperfect pun, we mean one which is heterographic or heterophonic, or both. And in fact, at least in English, the vast majority of puns out there are, well, if it is heterographic, then it's probably also heterophonic. So it's known that any given pair of words can be characterized by their similarity or their perceived similarity in terms of sound or pronunciation. So studying word pairs that are known to be related by some phonologically constrained process, such as punning or rhyming or erroneous production or what have you, can help us model the phonological rules at play in these processes or in language generally. And conversely, a model that quantifies the perceived sound similarity or difference between words can help us judge the likelihood or the acceptability of a given relationship between them, including the relationship of punning. So in particular, a model of sound similarity, which is tuned to puns, could then be used to help detect or generate them computationally. Now, one of the earliest and most influential studies on sound similarity of words is that of Witz and Winkler from 1973. So they started by producing an optimal alignment of phonemes between the two words, such that each phoneme is paired with either a single phoneme in the corresponding word or else with a null segment. They then compute the proportion of non-matching phoneme pairs, non-matching phoneme positions. They call this the predicted phonetic distance, or PPD. So for example, if we want to compute the distance between the word relation and underwritten, we would then first write out the phonemic transcription, as you see here, for relation, and here for underwritten, and we would align them optimally, pairing each phoneme with the closest one in the other word. And then we would observe that 9 out of these 11 positions don't match. Now, while this method correlates fairly well with human judgments, it was found to work much better if you apply it separately to the syllable onset, the syllable nucleus, and the syllable coda, and then take the average of that. So Witz and Winkler conclude then that perceived similarity owes a lot more to the syllable structure than it does to the individual phonemes. But a major flaw in this approach is that it glosses over the problem of aligning the two words to begin with. Producing this alignment of phonemes is actually a very difficult task. And it's one to which considerable research has been devoted, at least in the decades following this Witz and Winkler paper. Now, subsequent to Witz and Winkler, a lot of sound similarity models have been developed on the basis of shared articulatory features in the classic Chomskyan feature matrix. So while these systems are very elegant and they're very widely used, in practice, many sounds which humans judge to be similar can in fact differ in a very large number of features. So for example, in some feature spaces, the phonemes aya and aja would have 9 contrasting features, even though those sounds are close enough to be commonly confused by many speakers. And as further evidence of this, and to give an example which is a bit more relevant for our purposes, these two sounds, ya and ja, are not uncommonly contrasted in puns, at least in English, which is demonstrated by this example of a pun, which goes from yoke to joke. Trying to preserve his savoir-faire in a new restaurant, the guest looked down at the eggs the waiter had spilled in his lap and said brightly, "Well, I guess the yolk's on me." I guess the joke's on me. So there have been various attempts at mitigating this problem, ranging from the use of, say, multi-valued features or salience coefficients to the use of full-fledged linguistic theories like optimality theory. And these have been employed to various levels of success in, in related works, such as modeling the similarity of cognates, that is, of etymologically related words in different languages. And a few authors have tried to extend this general work on sound similarity by applying it specifically to puns. And this has resulted in a few articles and even a couple of book-length works. In 1974, for example, Franz Josef Hausmann, in his doctoral thesis, studied a collection of French puns and observed that the puns and targets never differed by more than 4 phonemes. This led subsequent researchers to posit that there was, well, some sort of upper limit on the number of phonemes you could have between the two phonological representations of a pun, or that is, between a pun and its target. There was a later study by Lagerquist, which agreed that when people make puns, they strive for homophony. They try to select the 2 words to be as similar as possible. And moreover, Lagerquist found that it was particularly important to preserve the number and the stress position of the syllables. She also observed that when a sound change does occur in punning, it always occurs, or almost always occurs, on a stressed syllable. Another somewhat later study by Zwicky and Zwicky, they observed that certain segments do not occur equally often in puns and targets. And they dub this phenomenon ousting. They say that Y ousts X when Y appears as a pun substitute for the latent target X significantly more often than the reverse. There was another book-length work by Walter Sobkowiak, who presented, I think it's actually the first time that anyone did an entire book-length study on the phonology of puns in 1991. He confirmed many of Lagerquist's findings, basically that, well, what I said before, but he extended this by concluding that the sound changes to consonants tend to prefer word initial and word final positions. Nonetheless, pun understanding is maximized when the consonantal skeleton is kept largely intact, whereas vowels carry a lower information load and are therefore more freely mutable. So as we've seen, there is no great shortage of past work on modeling the sound similarity of arbitrary pairs of words, or even on puns in particular, and by and large, the analyses that have been done tend to agree with one another. The main challenge for computational humorists, then, is how to consolidate all of this research into a single model that can be implemented computationally, and then applied to the generation or to the detection of puns in running electronic texts. So the first stab at that was in 2003 when Christian F. Hempelman, who's now a professor at Texas A&M University Commerce, took Sobkowiak's data and he used a modified version of optimality theory to model it into a computable cost function. And this function could then be conceivably used as the component in a program that generates or detects puns. But so far, no one has actually tried this, or at least not using Hempelman's model. But it was because no one had tried this that this year I'm co-organizing a shared task on pun detection and interpretation. So Professor Hempelman and I have produced a very large annotated data set of imperfect puns. That is, puns where the 2 words are spelled or pronounced differently. And we've solicited submissions from researchers to detect and interpret puns on this data set. So the results, if you're interested, are going to be compared and discussed at the Semival workshop to be held at this year's meeting of the Association for Computational Linguistics, which will be held August 3rd and 4th in Vancouver. So if you're interested, feel free to attend or just check out the proceedings. So wrapping up the talk then, In this talk, I have presented a method for applying lexical expansions to knowledge-based WSD, resulting in state-of-the-art performance. I have presented a method for merging the pairwise alignments of sense inventories, which turned out to boost the accuracy of knowledge-based WSD, and which can be used to cluster senses according to their semantic similarity. I've also produced a sense-annotated data set for puns, along with some pioneering algorithms for disambiguating them. And finally, I've presented a brief overview of the phonology of imperfect puns and the challenges in modeling them computationally. So that about wraps up my presentation. I want to thank you for your interest, and if anyone has any questions, I'd be happy to take them now. It was for measuring the agreement on the senses of the puns. Yeah, we had to use a somewhat modified version of it because, well, something called MASI. I don't know if you've heard of it. It's a way of comparing sense annotations using Krippendorff's alpha. So yeah, that's what we use it for. MASI. M-A-S-I. If you're interested, it's described in some of these papers. Well, which one? No, I guess I don't have the reference. Well, if you're interested, you can email me and I can tell you what it is.
Do you have, last part of it was very fun, kind of annotation, disambiguation into the puns. And do you have some kind of formal definition of the puns? So what are the boundaries of the data set of puns? And so how do you detect it?
Yeah, well, I mean, defining a pun is basically just two signs used in a language. It can be a word or a phrase, you know, where you have two separate but contrasting meanings, usually, but not always, for a humorous or rhetorical purpose. For constructing our data set, we had two different data sets. So we had the homographic data set where the two words were always spelled the same way, and we had another one where they were always spelled differently. We had a number of restrictions on the data set to make it easier for computers to process, so not quite real-world data. So first of all, rather than taking puns in running text, such as puns from the works of Shakespeare, we sourced only one-liners, just short jokes that are that you can understand in isolation. I think the average length of these punning jokes was about 10 or 11 words. Some of them, I think the longest one we had was something like 44, but most of them, the average was around 11. We also stipulated that the puns had to be a single word. We didn't want a phrase, though we did make an exception for phrasal verbs. So as long as there was only one content word in the pun, basically, only one noun, adjective, adverb, or verb, then it was admitted. We also disregarded inflections. So, if one of the words was cat and the other one was cats, then we accepted that. As long as the lemmas were the same, then we thought it was okay. What other restrictions did we have? The word had to exist in WordNet, and obviously to do the interpretation, the two senses also had to exist in WordNet. So our data set was actually quite a bit larger because we did identify a number of these puns that didn't meet the criteria. But we just basically whittled it down until we got something that the computers could work on. For the sum-eval work, we also made a distractor data set where we had a bunch of similar contexts, many of which were also funny. They might have been jokes or aphorisms or proverbs, but they didn't contain puns. But they were similar in length. They were otherwise relatively similar to the puns. And so in the sum-eval task, one of the tasks was indeed the detection of puns. This is why what I mentioned before when I said I might have been proved wrong. We had 3 tasks in that sum eval. We had the detection of puns, that is, given a sentence, does it contain a pun or doesn't it? And that's something I didn't do in my own work, but we got a lot of submissions on that. And I think accuracy was up to about 84% on the detection task, which is quite good. So maybe it's not quite as hard a task as I thought. The second task we had was location, which is given a sentence that we know contains a pun, the idea is for the computer to identify which word is the pun. The performance is a bit lower on that, but still fairly good. And the third task was the same one that I presented here, which is given a pun in context, we know which word is a pun, we want the computer to tell us what the 2 meanings are. And that proved to be a very hard task. And the system that I presented here in my own work remains the best performing system, at least by most metrics. A lot of people tried some supervised approaches, but the problem is that they had to manually annotate their own training data, which was very labor intensive. So, yeah. Sorry, did you want to follow up on your question? Hmm?
So you haven't taken into account cases when is it always token to token, one word to one word, pun to its target, or I'm thinking about cases when phonetically some subsequence is equal to other, but let's say the pun is one word and the target is several words, like ketchup and ketchup.
Yes, that's an excellent example, and that kind of example we would have admitted because in the admittedly artificial rules that we made, as long as the pun has only one content word, it's all right. So catch up as 2 words, that has one content word, catch. Up is a preposition, it's a particle of a phrasal verb, so we ignore that, we allow it. And catch up, the condiment, is also one word. So we would allow that. But if it's a longer phrase that includes more than one noun or more than one verb or whatever, then we would not allow that. But of course there are real world puns like that, and we saw hundreds and hundreds of them in the data set, or when we were compiling the data set, but we just excluded them from consideration because this is the first shared task of its kind, and we wanted to keep things simple for now. It's also the problem is that it's really hard to annotate that sort of thing as well for a human. How do you actually decide what word maps to what, and it gets really crazy really quickly, and so it's really important to keep things simple also for the humans. Other questions?
It's not an efficacy situation that we can see kind of ellipses in our past. If you look back to your example with delighted, and actually the first close context of the word delighted favors the sense like to be glad, some emotion. But then you will be, and then we can see an ellipsis.
Hmm?
However, if you don't, you will be
Yes.
then delighted.
Yes.
So, can you kind of can you system kind of suggest the place for the other for the ellipses here?
That would be a very good thing if it could do that. I mean, the system that I developed was purely lexical-semantic. It didn't rely in any way on syntax or higher level discourse stuff, no paradigmatics. But I admit that if the computer did have knowledge of that, it might help. But identifying, paronomasia is a particular rhetorical figure. Ellipsis is another one. And if you go back to classical antiquity, there was this very large collection of rhetorical figures that had been cataloged by ancient rhetoricians. And there has been a lot of work, well, I wouldn't say a lot, but there has been some work in identifying different kinds of these rhetorical figures. I'm not aware of anyone working on ellipsis, but if anyone had, then yeah, it could be maybe integrated into this and used to to find other rhetorical figures like paronomasia.
Any other questions?
Is it obligatory to have, for a button to have unemployment a word which is the source of the word? Is it obligatory to have two senses, or it could be more than two?
Yes, it can be more than two. The vast majority of puns have only two senses. Well, two distinct senses, I would say. We did encounter some in the data set. Unfortunately, I don't remember any off the top of my head, though I do remember it. It was a pun on the word key, where one of the senses, someone was making a musical joke. So one of the senses was a key, like the thing you put in a door. The other sense was a key, which is one of the levers on a piano that you use to play. And the other sense was a musical sense of key, like, you know, in the key of A, in the key of F, that sort of thing. So we did encounter a few of these puns, and again, we excluded them from consideration because we just assume that every pun has two senses. That said, that is somewhat of a simplification, even then, because when you look at a dictionary, especially one as fine-grained as WordNet, you often find that the senses, you know, two of the senses might be close enough in meaning that either one of them could be one of the meanings of the pun. So what we did was we allowed, for each meaning of the pun, the annotators could select as many WordNet senses as they want if it wasn't clear whether any one of them was meant. The only restriction was for the two meanings of the pun, the two sets of senses had to be distinct. And yes, quite often the annotators did select sets of senses rather than single senses for each meaning of the pun. But this is fairly standard in WSD evaluation campaigns anyway, that you allow the annotators to select sets of senses rather than individual ones. And basically, the machine needs to guess only one of the senses in order for it to be considered correct.
Any more questions? So I think if we don't have any more questions, let's thank you, Tristan, once again.
Thank you.